على مرتفعات الأردن يشيد مركز الأبحاث الجديد هذا. إنه مشروع فريد من نوعه يهدف إلى جمع العلماء من كافة أرجاء الشرق الأوسط. هذا ما يسمى سنكروترون، وهو جهاز متطور للغاية سوف يمثل نقلة في جهود الباحثين في هذه المنطقة، ولهذا فإن دولا كثيرة تدعم المشروع. هذا الموقع سوف يتيح للباحثين فرصة رؤية التفاصيل الصغيرة جدا كالفيروسات والذرات الدقيقة، ما ستكون له فوائد عديدة مثل اكتشاف طرق علاج جديدة. ولأن هذا هو الجهاز الوحيد من نوعه في الشرق الأوسط فإنه يجذب اهتمام بلدان مختلفة في المنطقة، بعضها عادة ما تكون معادية لبعضها البعض. المشروع الذي يسمى سيسمي تدعمه عدة دول عربية والفلسطينيون وإيران، وبشكل غير متوقع إسرائيل كذلك.
كان حلمي دائما أن يتمكن العرب والإسرائيليون من العمل معا من أجل فائدة الإنسانية وفائدة شعوبهم. كلا الجانبين مهتمان بذلك، وبالنسبة لي فإن سيسمي هو تحقيق لذلك الحلم.
وبما ترتفع حدة التوتر في المنطقة فإن العلماء يقولون بأن ما يهمهم هو البحث العلمي الذي يستطيعون القيام به، لا السياسة التي تفرق حكوماتهم.
ما نتمناه هو أن يفتح العلم الباب لتفاهم أكثر فيما يتعلق بقضايا أخرى. هذا ما نأمله. سوف نبدأ بالعلوم، وبطريقة ما سوف نفتح الأبواب التي كانت مغلقة لسنوات بل لقرون.
معظم المعدات التي تم تركيبها مستعملة، تم استيرادها من ألمانيا وبريطانيا، كما تم جمع مال بالكاد يكفي للمرحلة الثانية من البناء. من المدهش أنه رغم العنف بين إسرائيل وغزة فإن المشروع مستمر.
The international third-generation synchrotron light source, Sesame, is located in علان, 30 kilometers west of Amman, the capital of Jordan. The 2.5 GeV machine provides the user community with a wide range of synchrotron light, from infrared to hard X-ray with critical energy 6 keV. Sesame has been in operation for users community since July 2018. The operational electron beam current now is 300 milliamperes, while the design value is 400 milliamperes. Sesame injector is composed of 20 MeV classical microtron and 38.4 meters circumference, 800 MeV booster synchrotron. Sesame injector is that of BESI 1 machine. The booster synchrotron will accelerate the electrons to 800 MeV. Most of original BESI 1 parts still in operation, like the pulse elements and magnets, the power supplies, diagnostics and RF amplifiers, are renewed and refurbished. Due to the difference in height between the booster and storage ring, the ring-to-booster transfer line contains two vertical dipoles that increase beam height from 120 cm in the booster to 140 cm in the storage ring. The injection into the storage ring is done using only one dipole kicker, a scheme that is adopted for the sake of saving space and cost. Simple double-bend achromat, one composed of 16 mirror image cells with 16 dispersive sections. Each cell contains one combined function bending magnet flanked by 2 focusing quadrupoles, 2 defocusing ones, 2 focusing sextupoles, and 2 defocusing ones. The storage ring that contains 16 straight sections, half of them are 4.3 meter long, and the other half are 2.1 meter long, offers a maximum capacity of 25 beamlines. The storage ring is filled with electrons at 800 MeV at a repetition rate 1 Hz. Then its energy is ramped to the operational value 2.5 GeV. The RF system consists of 4 500 MHz Electra cavities, with maximum input power 100 kilowatts. The high-order modes in the cavity are controlled by cavity temperature and the plunger. The RF cavities are powered by 480 kilowatts. Solid-state amplifiers produced by Soleil and Sigma Phi consist of 165 RF modules in each tower. The RF plant is controlled by the digital low-level electronics from Dimtil. The storage ring is equipped with 64 beam position monitors, 48 of them are connected to Lebra Brilliance Plus electronics. The storage ring DCCT and FCT share same chamber and outer shield. There is one visible synchrotron radiation monitor in the storage ring, with a branch for interferometry. The ring also has an in-air X-ray detector IXed. One bunch-by-bunch kicker for both planes equipped with Lebra bunch-by-bunch, and one vertical scraper installed next to it. Sesame's first phase plan is to host 8 beamlines. 3 of them are currently operational, which are the X-ray absorption fine structure, X-ray fluorescence, infrared and material science. Another 2 beamlines, Beats and Hesab, are coming up to be commissioned next year, and the rest of them will be carried out in the following years. Sesame is the first and only light source to be fully powered by solar energy. A 7 megawatt solar power plant has been designed and commissioned in 2019, generating a total of 11.5 gigawatt-hour in its first year, and saving Sesame approximately $2.85 million per annum.
I'm a woman, thanks God, a Muslim, an Egyptian scientist, and I just moved from Italy to Jordan to work in an international research center called Sesame. Sesame aims to motivate scientific excellence in the Middle East, as it aims to bridge the gaps between people living in this politically conflicting region. So I'm here to let you know about these 2 aspects of the project. Sesame project all comes from a scientific fascination with light. For thousands of years, understanding of our universe remained restricted with what we were able to see with our eyes, and later with what we were able to see with tools such as microscopes. Hundreds of mysteries were revealed, yet seeing the invisible was and still is not an easy task. To see more is our inspiration to explore and to develop, and is our way to live and to survive. This motivated scientists to develop and construct super microscopes known as accelerators. Those have different shapes, forms, and technologies, aiming at spotting matter down to its atoms. The one I'm working on is called synchrotron light source. The technology has potential applications in life and material science, physics, chemistry, biology, and many others. It's so beautiful to see beyond the hidden unknowns, to answer so many questions about what lies inside us and around us, to view the past, the present, and to preview the future, and most importantly, to break a rule. So besides science, and inspired by CERN, Sesame also aims to connect people living in a boiling spot. Just imagine, to bring you closer, Arabic, Israeli, Iranians, Pakistani, and Turkish people sitting at the same table, not to negotiate about politics, borders, or peace treaties, but instead to talk about scientific collaborations. Annual meetings bring together scientists of the Middle East together with experts in one place. They simply think science, and when science talks, they listen. They may still be sitting as labeled groups, each representing a country, but at least for a few hours, they are looking at the same direction, to the same speaker, regardless of the political situation outside the conference room, regardless of the nationality or the religion of the speaker, exactly as we are doing now. In their own way, they are creating a certain kind of peace. You can find it outside. And this happens one meeting in a year and one step at a time. I got to see this during my first visit to Sesame in 2005 annual meeting. Like anyone else who knows very well the volcanic nature of that part of the planet Earth, best known as the Middle East, I had my doubts. It was an adventure. It didn't mean just a scientific conference. It meant something different. It was a usual scene to see participants from the Middle East gathering and chatting with experts in coffee breaks. The science presented during the meeting was impressive. But honestly, being in one place with those supposedly conflicting groups of people was adding something so much bigger, was adding a challenge. By the end of that meeting, I decided that I have to be a part of this community. And I did, after 10 years. 2012, I represented Egypt in Sesame Executive Committee.
Canadian Light Source is located at the University of Saskatchewan in Saskatoon. It was launched in 1999. More than 3,000 scientists have used the CLS more than 5,000 times.
A synchrotron is a source of brilliant light that scientists can use to gather information about the structural and chemical properties of materials at the molecular level. CLS consists of several components such as the electron gun, linear accelerator, booster ring, and storage ring.
The process begins in the electron gun. High voltage electricity, approximately 200,000 volts, is passed through a heated cathode to produce pulses of electrons. As electricity flows through the cathode, it will heat it until electrons are emitted. A nearby screen is given a short, strong positive charge which pulls the electrons away from the cathode. The electrons gathered from the electron gun are accelerated toward the linear accelerator, also known as LINAC. A series of cavities with microwave radio frequency fields in the LINAC provide energy to the electrons that are accelerated to an energy of 250 million electron volts. At this energy, the electrons are traveling at 99.9998% of the speed of light. The electrons are pushed by the microwaves. The LINAC produces pulses of electrons for 2 nanoseconds up to 140 nanoseconds for injection into the storage ring. The electrons must travel in a vacuum to avoid colliding into atoms or molecules and disappearing.
As the electrons circulate, they receive a boost in energy from 250 to 2,900 mega electron volts from microwave fields generated in the radio frequency cavity at 2856 MHz. The cylindrical RF cavity delivers a high energy kick to the electron bunches during each turn around the ring. It operates with a radio frequency of 500 MHz. The booster ring cannot increase the speed of the electrons to or beyond the speed of light, but the electrons now travel at about 99.99% of light speed. There are two types of electromagnets in the booster ring. The blue dipole magnets weigh over 3,000 kilograms. The magnetic field created by the magnets is used to direct the electrons around the booster ring. The field of the green four-pole magnets are used to force bunches of electrons into a fine beam within the vacuum chamber.
When the electrons reach 2,900 megaelectron volts, an injection system transfers them from the booster ring to the storage ring. The process repeats once per second up to 600 cycles, which is about 10 minutes, as required to reach an average circulating current of 250 megaamps. Once in the storage ring, the electrons will circulate for 4 to 12 hours, producing photons every time the 6,800 kilogram dipole magnets change the direction of the flow of the electrons. Some straight sections also include space for special magnets called insertion devices. While dipole magnets change the direction of the electrons, thus producing light, multi-magnet insertion devices called undulators and wigglers move the electrons back and forth many times, creating a narrow beam of much more intense light. A wiggler produces a wide range of high-energy X-rays. An undulator produces even higher intensity X-rays with a narrower range of energies. After each turn, there is a photon port to allow the light to travel down the beamlines.
The CLS has 13 beamlines for scientists to use. A beamline consists of an optics hutch. This is where the synchrotron light is focused and the wavelength is selected. Next, it follows into the experimentation hutch where the appropriate technique is selected for the experiment. Finally, in the workstations, scientists can operate the beamline and measure light as it is absorbed, reflected, refracted, or scattered by the sample.
In the optics hutch, there is a device known as the monochromator, which enables researchers to choose the wavelength of light. It separates different wavelengths using optical dispersion or diffraction.
Selected wavelengths of synchrotron light are focused by the mirrors in the optics hutch onto the sample in an end station.
Each end station is designed specifically for the types of experiments conducted on that beamline.
The synchrotron produces 13 different beamlines, some examples being biomedical imaging and therapy, resonant, elastic and inelastic soft X-ray scattering, and synchrotron laboratory for micro and nano devices.